All right, 20-4, we are going to talk about charges that are moving through a magnetic field. Before in 20-3, we had a current carrying conductor, which is just a conductor that has a bunch of charges ready to move. So now what happens if it's just an individual charge? They aren't contained to a path. So what they're experiencing based on their moving charge is a force. So now that moving charge, let's see, I'm going to have a charge. Now, when we do the right-hand rule, it has to do with a positive charge. So I'm just going to put a positive charge there. But if I have a charge that's moving, right, it's got a velocity. Okay, and with our right-hand rule, we've got a field direction, a charge direction as far as our fingers pointing towards it, and then the field direction, right, out towards page, whatever you want to call it, right? I guess it's in towards page here. But the force would still be the finger, and the velocity and the force itself, velocity and the force itself, are perpendicular to each other. So if I have a charge that's going at a certain velocity or speed, and it experiences a force that's perpendicular to it, I'm going to get circular motion, okay? First, conceptually, I've got a field that's going in, right? And if I have a charge that's entering the field, right, which way is it going to move, right? Which way is going to be directed when it's in the field? So I take my right-hand rule. If the field is into the page, oh, this is going to hurt. My direction, right, is to my right. Sorry, I have to put this at an angle. That means my force is up on the page. So my path for this is going to be, once it enters the field, it's going to create this circular motion, right? And then once it gets out the field, it'll go straight, okay? So positive charges deal with the right-hand rule, okay? Now we want to know what that force is, right? The magnitude of that force is related to the speed, right? The field itself, the field strength, and the charge itself. So the charge could be a positive 1e. Remember what E is? It's the charge of one electron, a fundamental charge. Now, charge of a proton is still that 1e, right? It's just positive. So I could have a 2e, a positive 2e. I could have a negative 3e if I wanted to, and just have an opposite effect, I guess is the right word. So what is our equation, right? Our force on that charge has to do with the charge, the speed of the charge, and the field, and then we still have that sine theta. So if the charge, instead of going in the board, were to come out of the board, that's when we would have this theta. So right now the charge is perpendicular to the field going in and out of the page, or into the page, horizontal or on the page, etc. So now, if this is the force, this is that centripetal force, and centripetal force is equal to the mass, v squared over r. So we can get these two equations together, and I'll just shoot that down, so that my centripetal force, I've got q v b, and we'll just say it's max, so we don't have that sine theta, equals m v squared over r. Speed of the charge, we cancel that out. I can figure out basically my radius of my motion if I know my field, my charge, and the mass of the object. Okay, so speed, right, mass, field strength, charge, I can find my radius. Okay, so or if I observe a radius, I experience a radius, and I know the charge, and I know the field strength, I can find, and the speed, I can find my mass. They use that in a thing called a mass spectrometer, and what I'm going to do is let you look at the Bozeman Science on Mass Spectrometers. There should be a little link to that just to show you the phenomena of how they use it. It's pretty cool. It's good to be familiar with that for any AP test. So, I'm trying to think what else we need to know about 20-4. Yeah, other than if it's for that positive charge, so if it's a negative charge, we go the other direction. I think that's it. I'm going to leave 25 and 26 to be the same video because they kind of talk about the same stuff. So, well, that's it.